This question is to present a two-part calculus problem focused on a continuous, positive function g, x, defined on the interval. Please subscribe to our YouTube channel Math Tutor 8285. Your subscription fuels the passion. Let's grow together. Copyright all rights reserved. Thank you so much. Let the function g of x be continuous on a closed interval from 0 to 1 and positive everywhere. Part 1. Prove that there exists a number eta between 0 and 1 such that the area of a right triangle having base eta and height g of et equals the area under the curve y equals g of x from x equals eta to x equals 1. Part 2. Suppose further that g is differentiable on the open interval from 0 to 1 and satisfies the inequality. The derivative of g is greater than negative 3 times g divided by x. Then the point eta found in part 1 is one of the following options. First step, setting up the equation. We express the geometric condition as an equation. The area of the triangle is 1/2 times eta times g of eta. The area under the curve is the integral of g of t from t equals eta to t equals 1. Therefore, we define a new function called psi of x equal to 1/2 times x times g of x minus the integral of g of t from t equals x to t equals 1. We need to show that psi of x has a 0 somewhere between 0 and 1. Next step out existence of the point eta. Let g of x represent the integral of g of t from t equals x to t equals 1. Then the derivative of g with respect to x equals negative g of x. Substituting this into the definition of psi, we find that psi of x equals negative 1/2 times the derivative of the product x times g of x. Now, define another function h of x equal to x times g of x. Notice that h of 0 equals 0 because x equals 0 makes the product 0. And h of 1 equals g of 1, which also equals 0 because the integral from 1 to 1 is 0. The function h is continuous on a closed interval and differentiable on the open interval. Therefore, by Rolle's theorem, there exists some number eta between 0 and 1 such that the derivative of h at eta equals 0. That means psi of eta equals 0. Hence, such a point eta exists. Next step. Uniqueness of the point eta. Now we differentiate psi of x. The derivative equals 1/2 times the sum of g of x and x times the derivative of g of x, plus an extra g of x from differentiating the integral term. After combining, this gives 1/2 times x times g prime of x plus 3/2 times g of x. Because we are told that g prime of x is greater than negative 3 times g of x divided by x, the whole expression for psi prime of x becomes greater than 0. Therefore, psi of x is strictly increasing on the interval. That means it can have at most 1 0. Since we already know 1 0 exists, it must be unique. Hence, the correct answer is A, always unique. When you face an existence problem involving both a function and an integral, introduce an auxiliary function whose derivative naturally leads to Rolle's theorem or the mean value theorem. That's the key insight here. Define it smartly,